Good morning, everyone. I'm Kaushik. I'm joined by my colleague, Nora, and we're going to talk about developing fine-grained geospatial units that reflect the built and natural world. Before going in, we are part of 2 Sigma, which is a financial sciences company based out of New York City. But unlike a typical financial company, most of our employees are data scientists and engineers, and they come from like various different backgrounds. We make use of this through the data clinic, and the data clinic is like a legal clinic in that we provide pro bono data science and engineering support to nonprofit organizations, academic institutions, government agencies, and so on. And these are on a one-off project basis with volunteers from rest of 2 Sigma, like Nora, giving up a bit of their time to work on these projects. We're going to talk about one such project and some of our open source work that we do as well. Just to give you a sort of hint at sort of what kind of work we do, a lot of open data is geospatial, and a lot of questions that organizations, nonprofit organizations have are geospatial in nature, and they don't have the resources to do geospatial analysis. So a lot of our work ends up being geospatial in nature. We have worked with the Arts Agency of Nashville to try and understand whether their arts programming is equitable across the city, doing a little bit of catchment analysis, understanding the populations and distributions across the city. We've also worked with the Vera Institute of Justice, which is a criminal justice reform policy organization, and we have helped them gather 911 data from various different cities in the US so that they could do more interesting temporal and spatial analysis with this. But this talk today is going to be about one of our more recent projects that we are continuing to work on right now, which is developing open source geospatial units in Denmark. And this is a collaborative unit, collaborative work between us at Data Clinic and Aalborg University, particularly the Department of Built Environment, which works on these topics of urban development, built environment, sustainability, and planning. And they have this project with the goal of understanding quality of life within Denmark and the various aspects of it and trying to map this across the country. And they're doing this with us, and we are helping them out with this project with support from other organizations, particularly Statistics Denmark, who are providing the data, and particularly for these sort of quality of life metrics, individual level data to make even this sort of analysis possible. And there are other collaborators as well, such as the Data.org, MasterCard, Center for Inclusive Growth, and the Rockefeller Foundation, who have sponsored through the Inclusive Growth and Recovery Challenge, the sort of funding for this project. And last but not the least, there are important stakeholders for this project. So Danish municipalities, local organizations, decision makers, and researchers who we are building this tool for to make this data accessible, because we want this data and insights to lead to action within the country. So that's the sort of high-level outline. I'm going to pass it over to Nora now to go into a little bit more detail about the project.
Thank you, Kaushik. Here from this slide, I'm going to start giving a more detailed overview about the project that we partner with Aalborg University to work on, which is creating granular open source geospatial units for Denmark. So the ultimate goal and the motivation of this project is we want to empower data-informed action for more equitable economic opportunity across Denmark. To do that, we want to present the data and the analysis results on socially meaningful and granular enough geospatial units. However, what we have right now in Denmark are municipalities files that are too large in shapes. For example, we can see various socioeconomic environment from place to place in just one municipality. Thus, the insights do not facilitate tailored action. In other words, the municipalities are too large and not granular enough. We do have super granular data, though, in Denmark that is at 100 meter by 100 meter grid level. For example, we have population and household count associated with those grid cell level data. However, those data do not meet privacy constraints, and then it's very limited for general public and policymakers to use. Therefore, these data are too granular to be usable by them. Therefore, what we need is we want to create polygons that is more granular than municipalities and less granular than the grid cell level data. And we also want the polygons we create to reflect physical boundaries and to meet all the privacy constraints. And that is why we start this project. Before we started our process, we actually just tried to simply cluster the grid cell data. And the results here show that it does not work at all. On the image here, you can see there are many oddly shaped clusters. The reason is there are many grid cells with zero population and household count, so the clustering algorithm will just randomly assign those grid cells to different clusters, creating these pretty long and oddly shaped polygons, which is not very useful for research and analysis. This gives us motivation to start our own process and also gives us confidence that our approach will definitely work better than this. And our first step here is we want to build polygons that is socially meaningful and also reflect the built environment. We're going to do this by starting building a hierarchy of socially meaningful polygons. And the input data here are all open source data. One is the road network from OpenStreetMaps, and we also will use the municipality borders from the Danish Open Data Portal. On the image here, you can see this is one of the municipalities in Denmark, and there are different levels of road network represented by different thickness here. And we can utilize these different levels of road network to break down our municipality. We will take an iterative approach. The first step is we use the primary roads to overlay on the municipality shape to break it down to 3 big regions. We can further apply secondary roads to further divide the area to smaller shapes. And this is super similar to US Census tract level. And finally, we can overlay the remaining residential and unclassified roads. And here we can create more granular shapes that is similar to US Census block group. The benefit here of creating different levels of polygons is now we can do research and analysis at different geographic granularity. And also when the researchers and policymakers want to view the results, they can choose the level as they wish. After we created these polygons, we are on the next step, which is mapping the grid level population and household count values to the polygons we created. The most straightforward way here is we can just simply spatial join in the grid cells with the polygons, but this approach will require some interpolation. So although this approach can preserve the smooth polygon boundaries in the end product, we need to make assumption about the population distribution in the grid cells, which sometimes is pretty hard. So we think about another option, which is doing a simple grid overlay. And this approach does not require any interpolation. So we can retain pretty accurate population and household count information. The trade-off there, though, is we will see the shapes becomes less natural. A little bit recap of our ultimate goal. We want to present all the data and analysis results on the spatial units for the policymaker to make actionable, for them to have actionable insights. Therefore, the accuracy of the data is the most important thing that we care about. So we decided to go with option 2. Now we have polygons and we map the values to the polygons. We are onto the last step, which is clustering. And we actually choose the max-P clustering algorithm. This is helpful because we can set a threshold that each cluster region in the end will have at least 150 individuals and 75 households so that we can meet the privacy constraints. So the data is actually usable by general public and the policymakers. We also use the Rook's contiguity as the spatial weights. So the polygons will look more natural and more compact, and it's more similar to what we picture as neighborhoods. We evaluated the results to ensure that the privacy criteria will be met in the last 10 years. so that for any future time series analysis, we know the polygons is usable and the research analysis is meaningful. Again, we will also check the compactness of the resulting regions, and we will also do visual checks for all the municipalities in Denmark to ensure the results is meaningful and is desirable. With that, we now created the polygons, and then we created the geospatial units of different levels, and we will present it in a website format. And with that, I'm going to hand it over back to Kaushik to talk about the end product and the future vision and next step of this project.
Thanks, Nora. So as you can see, the team at Aalborg University is working hard to develop a website which uses these geospatial units that we have created, integrate into a website so that key metrics around quality of life, such as education, like income and migration and transportation and all these different metrics are made available to the Danish sort of municipalities, government agencies, and policy researchers in the country. This is just like a demo and some screenshots from a work in development, so there's still like missing pieces in there. But the team is working hard at Aalborg to get this website released in Denmark in early 2023, so keep an eye out for that. There are a few more steps involved in getting this project to completion. Right now we are using data for the last 10 years, but Danish policy or regulations require that these polygons are consistent over the last 30 years or ensure data privacy over the last 30 years. So we are looking to expand our data window there, do a little bit more of longitudinal analysis to ensure these are consistent over time, and integrate feedback from stakeholders, because we are doing this from a very data science perspective. Obviously, people who work in these regions might have different perspectives on this. But the end goal of this is to get these units and these hierarchy of units adapted as the standard unit of analysis for Denmark, similar to how we do in this country, where naturally when we think of geospatial units, we think of census tracts and census block groups and stuff like that. So trying to build something similar for Denmark. We've also open sourcing the pieces of this work. So the polygonization library, the link is there, and we have the regionalization work in another repo. We want to build these out in both R and Python so that folks can use pieces of this in their own work. And we're looking to sort of scale this application to other use cases as well. This is not only for Denmark. We're thinking about aggregating estimates from WorldPop, which are satellite imagery-based population estimates, and aggregating them to more meaningful regions for countries where population data is heavily limited and like grid cell level data is hard to use for organizations on the ground. And we're doing this because open source is a key part of our mission at the Data Clinic. We want to open source work, and we want to put our work out there so others can use it and build on top, and we can build together. There are a couple of other tools that are in early development from us at Data Clinic. One is NeoHoods, which we briefly spoke about at the last Spatial Data Science Conference, like 3 years ago, really, which is a web-based tool and Python library to cluster feature data while maintaining spatial contiguity. And then we're also now working on disaggregated population estimates, where based on building footprint data and population counts from the census, we can disaggregate these populations to the building level so that we can provide this to folks working with this data for custom geographies, so that you don't have to do aerial interpolation all the time, and these estimates are much more accurate. And that's it from us. Nora and I are here, but Sixten, who's an important collaborator in this project, is also here. Do you want us to stand up and wave at everyone? So you can come reach out to us and talk to us more about this project later. But thank you all for your time.